As we defined before, every sound source has some power. So what is power? At what rate energy is transferred from one point to another? If we are talking about the source sound power, so how quickly energy is transferred from our vocal cord to the air. It's defining the power of my sound. Or a loudspeaker. How quickly this sound power is transferred from speaker to the environment, to the room. It is defining the sound power. And the power equation definition is the same for all types of powers. The rate at which energy is transferred is called power. So if a quantum definition starts by the rate, absolutely, there is going to be a delta T in denominator, so we are going to divide how much energy is transferred in how many seconds. This is going to define the power of that mechanism, whatever it is, a source of sound power. If it's another source, electric power. Another wave power. The unit of the power is watt, and according to this equation, 1 watt is equal to 1 watt is equal to energy is joule, 1 joule divided by second. And power, of course, sound power, of course, determines how loud you are going to hear a sound. But only quantity which determines how loud you are going to hear a sound is not the power. Also, distance. If you are close to a sound source, just like this listener, you are going to hear a louder sound. But if you are far from a sound source, you are going to hear a softer sound. Yani, as distance increases, so you are going to hear the sound softer. As distance decreases, you are going to hear a sound louder. But why? Why is it so? How can we explain this by physical quantities? We will explain this by a quantity known as wave intensity or sound intensity or sound intensity. It is very similar how light becomes less intense when it moves from a source. Look at this. There is a sound light source, and there are 1, 2, 3 surfaces. But the first surface area is small. Second surface area is large. Third one is larger. So what happened? So this area, as area is small, because the energy coming from the source is distributed in a small area, intensity of the light is big. But as area increases, so this time the same energy leaving this source is distributed over a larger area, intensity decreases. And for the last one, which is the farthest, the area over which the energy is distributed gets largest, intensity is smallest. Sound is also expanding in a similar way. When there is a sound source in here at this origin right here, of course it's expanding in all directions as compressions. We know it. Sound is expanding as compressions, and these compressions are expanding in all directions like a sphere. Of course, for initially when the sound is sent, compression is so close to the source. Energy sent by the source is distributed over this small area. Area of the sphere is not that big. But as compression expanding, this area gets larger. Same energy this time will be distributed on a larger area. So of course separation between the, as you see the rays, remember rays are indicating direction of the wave motion. So is increasing. Yeah, the intensity is decreasing because area is increasing. The area gets much larger and then larger. So as area of this sphere increases, intensity, like sound intensity over this area is decreasing. Because the sound power propagates equally in all directions, the power emitted by the source is distributed over a larger area as wavefront expands. which makes intensity smaller. As a result, wave intensity of the sound decreases as distance from the source increases. Then we will continue with definition of the wave intensity. It is I, capital I, is just like moment of inertia, but of course there are different quantities. Wave intensity of the sound is defined as the rate at which energy of a plane wave flows through an area. The rate at which energy flows is called power. It's the definition of the power. So, through a unit area, and you are going to divide power by area. If you divide power by area, you are going to calculate sound intensity or wave intensity of the sound. Then I is equal to P, power of the sound source, divided by area over which this power is distributed. We can find what the sound intensity or wave intensity is. Its unit is watt per meter squared, because power is watt, area is meter squared. Watt per meter squared is the unit of sound intensity or wave intensity of the sound. Because sound wave is distributed over a larger or a spherical surface, because we know as the sound is expanding, it's expanding as a sphere. Compressions are expanding as spheres. So I am going to insert in this area of a sphere, surface of the sphere. Sphere surface, spherical shell. Area of the spherical shell is 4 pi r squared. Then we are going to insert, instead of area, what? 4 pi r squared. Then we can find sound intensity depending on the distance from the source. Because where the compression is, it is the distance from the source, which is represented by r. It is at the same time radius of this sphere, 4 pi r squared. And this equation tells you that sound intensity is directly proportional to power. As power increases, sound intensity proportionally increases. Yani, how can we change the power? Maybe there is one speaker, you can add one more speaker. You double the number of sound sources. As the number of sound sources increases, power of the source proportionally increases. One of them is this. Wave intensity of the sound increases as the power of the sound source increases, and directly proportional to power. Second factor which affects the sound intensity is the distance. But distance is r from the sound source, which is at the same time radius of the compression, that sphere which is distributed around us. So inversely proportional to square of the distance from the sound source. Wave intensity of the sound decreases as distance from the source increases, and inversely proportional to square of the distance, r squared, or directly proportional to 1 over r squared. Inversely proportional to r squared, directly proportional to 1 over r squared. Remember from chapter 1, section 3, we know the difference between these two. Okay, now I'm going to solve problems about this. Easy ones I left for you, but two problems are generally you struggle when we meet sound intensity. One of them is, by what factor does the distance change from the sound source if the sound intensity becomes 5 times the original intensity? So, intensity of the sound changes. To make this change, what should be the distance? Distance change. What should we talk about this? So I know how sound intensity and distance related. I is proportional to 1 over r squared, or inversely proportional to r squared. Question tells you that we are going to make this sound intensity I 5 times the original. Yani change factor of I should be 5. 5 times means 5 is the change factor. So I am going to add 5 as a change factor I. So I changes to 5i. But in mathematics, in one side is multiplied by a number, of the proportionality. Other side also multiply by the same number. Yani, I have to also add this 5 in here. 5 times 1 over r squared. So what is this 5? This 5 is the change factor of 1 over r squared. Question is asking you, by what factor distance change? Yani, what is the change factor of distance? But I can find this. This tells you that 1 over r squared has a change factor of how much? 5. Then the rest of them is mathematics. If 1 over r squared has a change factor of 5, then 5 over 1 in fact, r squared should have a change factor 1 over 5. Still we didn't get the answer. This question is asking not r squared change factor. Change factor of r. So what should we do? So I have to take the root. Root of r squared is r. So I should take the root of other side as well. Root of 1 over 5, 1 over root 5. Yani change factor of r is going to be 1 over root 5. So B is the answer for this question. And 11, another one. These two questions are generally you are asking me frequently. This I will slow down. What is the ratio? Ratio means division. What is the ratio? So I had to draw a division line. Ratio of what is coming after of is going to be in numerator. You know that. Intensity of sound intensity at a distance of 4 meters to sound intensity at a distance of 2 meters. Yeah, there are two distances. So there should be two sound intensity. First one I am going to say R1, distance 1. Sound intensity at distances I am going to say I1. Second distance, 2 meters, I will say R2. Sound intensity at distances I am going to say I2. What are they asking? What is the ratio? I1. Of, after all, I1 is coming, I will write it in numerator. 2 what? Distance on sound at the distance on I2. What is coming after 2? Must be written in denominator. Okay, I1 over I2 is the question. Okay, I know that I1 or I2, whatever, proportional to 1 over R squared. Yeah, instead of I1, I am going to write 1 over R1 squared. Instead of I2, I will write 1 over R2 squared. Why didn't I write power and 4 pi? Because they are same for both. When I write them, they will simplify. Why should I write again? Because they will simplify. So instead of I1, I am going to write all the variables. 1 over R1 squared divided by 1 over R2 squared. Then flip them. You will get the result like this. 1 over R1 squared is the numerator multiplied by the denominator must be flipped and multiplied R2 squared divided by which becomes R2 over R1. Both have squared. We can get common square for both. Then I found it. I1 over I2 is equal to R2 squared divided by R1 squared. Then insert the number. I1 over I2. How much is R2? How much is R2? 2 meters. How much is R1? 4 meters. 2 over 4 squared. 2 over 4, 1 over 2. Square of 1 over 2, 1 over 4 is the answer for this question. And these are two common questions which generally asked to me. That's why I solved once again. Then, audibility. Every sound is not audible for us. Some sounds are audible for human, some not. Depends on the frequency. So, we as a human hear sound between 20 and 20,000 hertz, we know from section 1, which is the audible range. But this is one of the factors to make the sound audible, but not the only factor. There is one more factor To make this sound audible, intensity, sound must be on your ear, high enough intense to make it audible. Second factor is wave intensity of the sound around your ear. If the sound has enough intensity, and this range has enough intensity, we can hear it. If intensity is not enough, even though it's an audible range, you cannot hear that sound. And maybe many years, maybe 100 years, maybe decades, I don't know, they make a table. This table defines us, for human, which intensity, which frequency of the sound is audible at what intensity. Horizontal axis will represent the frequency of the sound, vertical axis will represent wave intensity of the sound. And we are going to study a diagram which defines audibility. This diagram, as you see, horizontal axis is frequency. And it is between 20 Hz and 20,000 Hz, it's audible sound. But this frequency is not only a factor which affects the audibility. Also, intensity. Intensity changes between 10 to the power of negative 12 and 1 watt per meter square. So, this frequency must have a sufficient intensity to be audible. So this diagram is defining that. Which sound is audible, at what intensity and frequency, we are going to see in this diagram. This region, inside this curve I draw, is area of the sound. Yani, any sound inside this region is going to be audible for us. For example, let me choose a sound. This sound is audible. This sound is also audible. That sound is also audible. Let's check their frequencies and intensity. 100 Hz. Intensity 10 to the power of negative 12 is audible. Or another sound, what is frequency? 1 kilohertz and 1000 Hz, and then intensity 10 to the power negative 2 audible. Or another sound, C, is 1 kilohertz, yani 1000 Hz, and then intensity of 10 to the power negative 12 audible. This is the area of the sound. Inside this area, every sound is audible. But if we have a point outside this curve, for example here, or for example here, these are not audible for us. What are they? For example, this sound. 20 Hz, and then intensity 10 to the power of negative 12, not audible. For example, this one. 20 Hz at 10 to the power negative 8, not audible. 100 Hz and then intensity 10 to the power negative 10, not audible. Audibility starts from this blue curve on. Yani, if I choose a point on this curve, for example, this point, this is an audible sound. This is an audible sound. This is an audible sound. What are those sounds? Look at them. 50 Hz and an intensity of 10 to the power of negative 7. Audible. Audible starts. Or 100 Hz and an intensity 10 to the power of negative 9 or close to negative 7. Audible. Or 500 Hz and an intensity of 10 to the power negative 12. Audibility starts. I said audible starts, not audible only here. Audible here or above. Audible here or above intensity. Audible here or above intensity. That's why this blue curve is known as threshold of hearing. Yani hearing starts on this blue curve. And above is also audible. But below, not. Not below than this intensity. not audible below that is intensity. Not audible below this intensity. So, the sound of every different frequency has a minimum wave intensity to be audible, known as threshold of hearing. And softest sounds, the smallest intensity of the sound we hear as a human, happens at a frequency of 1000 hertz, and this sound is 10 to the power of negative 12 watt per meter square intensity it has. This number is known as threshold of hearing. Threshold of hearing, yani softest sound we can hear. But there is a red curve, as you see. This red curve is called threshold of pain, which means in here, when you count this mega intensity at this or above, so it is dangerous. If the sound intensity becomes greater than this number, which is 1 watt per meter square, so you can be sudden death. Threshold of pain. What is the number of threshold of pain? 1 watt per meter square, we have to know it. What is the number for softest sound which we can hear, threshold of hearing? 10 to the power of negative 12 watt per meter square. But one more thing we see. When the frequency of the sound is between 500 hertz and almost 7 kilohertz, yani 7000 hertz, intensity of the sound is smallest. Middle. But less than 500 hertz frequency. What's happening in intensity? Look at that. 200, intensity should increase. 100, increase more. 50, again increases. As frequency decreasing from 500 to 20, to make these sounds audible, you should increase the intensity. So that's why it's written that sound at low frequencies, yeah, less than 500, must have high intensity to make them audible. Not only so low frequency. Look at the other side. Yes, 7,000 audible at 10 to the power negative 12, but 10,000 greater than this. 15,000 10 to the power negative 10. What's happening to the intensity? Also should increase to make these sounds audible. That's why we said that sounds at low frequencies, yani this side, or high frequencies, yani that side, must have intense to be heard. But in the middle, right here, it is the smallest intensity. However, sounds in the middle of the spectrum are audible at lower intensities. Low frequency needs high intensity to be audible. Higher than 7K needs high intensity for audible. But between them, we need a low intensity to make the sounds audible. As we said, greater than 1 watt per meter square is dangerous, sudden death. But even not greater than that, less than 1 watt per meter square can also be dangerous if you listen that sound in a long time, prolonged exposure. Is that? Rock musicians, they wear earplugs to block the wave to enter their eardrum. So they decrease the sound intensity by this way. So for this reason, many rock musicians wear earplugs during the performance to decrease the intensity of the sound on the eardrum. And relative intensity. So sound intensity, we got it. Sound intensity depends on two factors. One of them is power of the source. Second one is distance from the source. But what is relative intensity? Why did they needed such a quantity to define relative intensity. It's about sensation of the loudness in your ear. How loud a sound can be detected by your ear. It's about that. And loudness. Relative intensity or loudness or decibel level, they are equivalent to each other. Relative intensity, decibel level, or loud. All are represented by beta. Here's a loudspeaker, as you see, whose power is 5 watts. And at a distance of t from the source, there is someone listening to that sound. And this source produces around this ear an intensity of I. If you add one more speaker, what happens to the power? Power doubles. And we know that intensity and power directly proportional. Yes. Sound intensity, yani energy per area. Sound intensity short definition. Energy per area. Power per area. Also doubling. It also doubles. Yani power of the sound arriving your ear is also doubling. But loudness, which means how loud you can detect the sound as a human, is not doubling. It's increasing, but not doubling. It is not 2 beta. Even I is doubled, I to 2I, but beta is not doubling. It's beta to 2, not 2 beta. It's less than twice of the beta. So loudness increases but not doubling. But why is this so? It's about how ear or human ear is created or designed. So sound A is twice the power of the sound B, twice intensity of the sound B, but not twice as loud as sound B. Sound A is not twice as loud as sound B. Why so? It's about, as I said, design of the human ear. Sensation of the loudness in human ear is logarithmic. Logarithmic function is a surprising function as it's, you see, domain. Domain doubling, range does not double. Or just like in mathematics, domain is x, range is 1. Was it like this? If domain is doubling, range is not doubling. It's increasing but not doubling. Logarithmic function is something like this. Do you remember how you draw it in the 11th grade? That function was like this. Yani as domain is doubling, range is not doubling. It's increasing but not doubling. So same thing happens in here. Even though we double the intensity, but loudness will not. Okay, then we are going to define relative intensity. What is relative intensity? How can we define it? Loudness or relative intensity or decibel level, beta, is not directly proportional to sound intensity, is not directly proportional to power. So relation between loudness and relative intensity and sound intensity is logarithmic. Then now we are going to make a new measurement. We are measuring the loudness by beta. Softest sound is decided to have a relative intensity 0 decibel. Softest sound is the sound which we hear. Softer than that, we cannot. Its intensity was 10 to the power of -12 watt per meter square. And this sound intensity is defined to be as 0 decibel. This is just a scale done by us. Then we are going to compare other sounds to this softest sound. Because our hearing starts with this sound. That's what we made here. Then we are going to compare other sounds to this one. Then relative intensity beta of any sound at a certain point is defined as logarithmic ratio of the intensity of a given sound to intensity or threshold of hearing. Logarithmic ratio. Yani it's going to be a ratio, absolutely. We are going to compare a sound to softest sound. Any sound we will compare. Compare means divide by softest sound. But it's a ratio, but logarithmic, so there will be a log function. This number is very small number, 1 point something, 1 point something. Separate, the increase is not so big. That's why they multiply this function by 10 to make this increase noticeable. This 10 is no other meaning. Yeah, it was 1.2, 1.3, 1.5, 1.4, 1 point something, or 0.65, 0.67. If you multiply this, 6.5. Now 6.5 becomes 65. Yani to make that difference between the beta noticeable, we multiply this log function by 10. That's the only reason why. Then equation for relative intensity happens 10 times log I over IO. Example. What is the relative intensity of sound at threshold of pain? I am going to compare threshold of pain to threshold of hearing. Then I will calculate its relative intensity. So let's use this equation and compare them. But this comparison is going to be logarithmic, not the comparison that we know direct proportionality. So then I will write beta is equal to 10 log. How much is I for threshold of pain? 1 watt per meter square. How much is threshold of hearing? 10 to the power of negative 12. If you use your calculator, yes you can, you will get the answer as 120 decibel. So, threshold of pain, loudest sound. Its intensity, 1 watt per meter square. What is relative intensity? 120 decibel. So, greater than this relative intensity or decibel level, it is dangerous. You can be deaf, sudden deaf, if the sound is greater than 120 decibel around you. This is how we can calculate relative intensity from a sound intensity, given sound intensity. But what if the question is not this? From relative intensity, calculate the sound intensity. If decibel level is given, how can you calculate sound intensity? We can use again logarithmic function. We can use logarithm. So it is beta is equal to 10 log I over IO. Calculate first I over IO. We can do that. Beta is how much? 30. 10 log I over IO. Then divide by 10, divide by 10. So then log I over IO is going to be 3. Then we are going to use your calculator. Shift log 3 will give I over IO. Shift means inverse. Log inverse 3. It's going to be 10 to the power of 3. I over IO 10 to the power of 3. After that cross product, IO and 10 to the power of 3. So I is going to be IO 10 to the power of negative 12. So multiply by 10 to the power of 3. Result is going to be 10 to the power of negative 9 watt per meter square. One of them is this. Second one is we can use a short way. If sound intensity is given to you, or relative intensity is given to you, you can calculate sound intensity by this. 10 beta minus 120 divided by 10 is the exponent power of this 10. For example, let's apply this question. 30. 10 beta is 30 minus 120 divided by 10. Result is the power. 30 minus 120, negative 90. Divide by 10, negative 9. 10 to the power of negative 9 watt per meter square is 30 decibel. For example, 60 decibel. 60 decibel. How much sound intensity is this? I, 10 log, beta. How much is beta? 60. Minus, how much is the loudest sound decibel level? 120. Divided by 10. So this is negative 60 divided by 10. 10 to the power of negative 6 watt per meter square. And you can find this way also without using logarithmic way of the sound intensity. Another question, Mr. Question. When decibel level of the traffic goes from 30 decibel to 60 decibel. From 30 decibel, from an initial value of 30, it goes to a final decibel level, 60. How much greater the intensity of the noise? Intensity of the noise means I. How much greater is I? Yeah, I final over I initial is the question. How much greater when we say we should compare that? How much greater? Not the factor, the ratio. So I can find this. I final over I initial. First, I have to find how much is 6 decibel in relative sound intensity. We found it. 6 decibel. How much sound intensity? 10 to the power of negative 6. 10 to the power of negative 6. Divided by. Initial is 30. 30 decibel is how much sound intensity? 10 to the power of negative 9. Result is going to be 10 to the power of 3. And you can go this way. Or, just for this type of question, one easy way, for example, this one. When decibel level of traffic in a street goes from 30 decibel beta initial to 50 decibel beta final, how much greater the intensity of the noise? Again, we will find I final over. You can calculate I initial, you can calculate I final, then you can divide them. Or a short way, but just the short way, we are going to solve it. I final over I initial is going to be. First type, what is B final over B initial? B final is how much? It is 50 decibel. B initial is how much? Which is 30 decibel. We will find I final over I initial. Write 10 and 10, this is just for result. Remove 1, 0. Take this 5 here as a power. Take this 3 here as a power. Result is 10 to the power of 2. 100 times greater the intensity of the noise. This is the shortest way. You don't need to deal with this again, calculate I initial, calculate I final, then divide that. If you know beta final, beta initial, remove 1, 0, 5 in a year, but don't forget they are not equal to each other. Yani, I final is not 10 to the power of 5. I initial is not 10 to the power of 2. This is hack to get the same result in a short way. And one problem, we are going to finish this title. A noise emission factor produces decibel varying 80 decibel. This is initial decibel level, beta initial. And these beta initials provided only by one machine, N noise emission. If I label number of emission by N, because something is numbered, we are generally shown by N, and initial is going to be 1. How many identical emissions could we add to the factory without exceeding 90 decibel? Then beta final is going to be 90 decibel. I know that sound intensity is directly proportional to power. Power is directly proportional to number of machines. Number of machines and sound intensity directly proportional. Yeah, if I want to know how many machines are added, I should first find number of the final number of machines. Then let's find this. Beta final. How much is beta final should be? 90 decibel. How much is beta initial? 8 decibel. So I can get I final over initial. Can I get it? Yes, I can. Yes. But again, by hand way I am going to use. Remove 1, 0. 10 to the power of divided by 10 to the power of, result is 10 over 1. Why did I write rational number? Because I want to make this I final initial, which is the sound intensity, also equal to n final over and initial. Because number of machines and sound intensity are directly proportional, yani 10 over 1. So initial number of machines, how many? Is it correct? Initial how many? Then finals how many? 10. So question is not asking what is final number of machines. If the question was what is final number of machines, it would be 10. But how many added they're asking? Of course, added machines, final minus initial. The final is 10, initial was 1. Result? 9 machines should be added. Tamam? Evet, sanırım bir tek yaz oransı kaldı. Bunu da yapalım. Let's do this one also. Intensity of the sound may be increased by 1000. Increased by 1000. Final intensity divided by is 1000. Increased by 1000. What is this increase in decibel? Yani increase in decibel, delta beta is the question. Delta beta. And what is delta beta? Beta final minus beta initial. I can arrange the equation of beta to this question this way. Beta final over beta initial is equal to 10 log I final over I initial. This is similar to how we calculate the relative intensity of any sound. But in there, instead of I initial, there was IO. It was IO, but this was beta O. Beta O is 0. We don't write it. In fact, this equation, that equation, same equation. So let's find how much is delta beta. How much increase equal to decibels? Let's find this. Log, I final H 1,000. 10 log 1000. And so log 10,000, 3. 10 times 3. Delta beta is going to be 30 decibel. We can also do it this way. Ya da short way for this type of question. Write this by exponential number 10 to the power of 3, değil mi? I final I initial. So delta beta, take this in here to 1, 0. But only this type of question. If they give you increasing intensity 1000, how much is the increase in decibel? 1000 is 10 to the power of 3. 3 down there, we put 1, 0, 30 decibel.
Eğer decrease olsaydı negatif olacaktı.
Decrease olsa negatif olurdu tabii ki. Change was negative with decrease. Negative 30 decibel. Tamam mı?